Let's start with understanding angles first. Angles are everywhere. For example, corners of a room where two walls meet create an angle. A ladder leaning against a wall creates an angle with the floor and also with the wall. Your bent elbow creates an angle. Angles are that simple. Let me introduce more formal and boring definition. If I take a ray originating at point O and extend it up to point A, I have a ray OA. Let me call this the initial side and let me make a copy of this and call the copied line as OB and rotate OB keeping O as the center. We see an angle created here. Note that the ray OB is called the terminal side. Angle is basically the corner created by the ray when its copy is rotated from the same initial point. Let me refresh your memory about how angles are measured. You are right, your good old friend protractor to rescue. You place the protractor so that the angle you want to measure coincides with the origin marked in the protractor. Let's look at these examples. So this one is a 60-degree angle. In this example, the origin coincides with a 90-degree line, so it's a right angle. This looks like which is beyond 90 degree. Let's measure it. Okay, this is 120 degree. This looks like a perfect straight line. In this example, base of the protractor coincided with the line, so it's a 180 degree. So far all the examples we had measured angles in the anti-clockwise direction, but this example is quite different. So we are measuring the angles in the clockwise direction. So the sign of this angle becomes negative. So it's negative 75 degree. But let me tell you, measuring angles in degrees has some drawbacks. Some scholars call it's not the pure measure of angle. What if you want to measure angle which is less than 1 degree? You might say I can measure in minutes and seconds, but that are not elegant. Why should be a circle divided into 360 degrees? Why not 100 or 1000? For some historical reasons, our ancestors have used 360 degrees for one full rotation. That doesn't mean we should use the same norm. In fact, they're a better and elegant measure of an angle. Okay, before learning about this new angle measure, let's do some activity. Here I have taken some colored circles. In this case, this red circle I have cut into two equal parts. Okay, if I place it one above the other, these two sectors perfectly coincide. So by this, can we say, so the angle at the center of the sector is half of the angle of the full circle, that is 180 degrees. Similarly, arc length of each sector will become half of the perimeter, which is half times 2 pi r. Notice here instead of writing 1 by 2, I have made a clever substitution. I've written as 180 over 360 times 2 pi r. I'll tell you the reason why. Okay. Similarly, for area of each sector, we can call it as half the area of the circle. Right? So I can write it down as 180 degree by 360 degree times pi r square. Let's look at another example now. Here I have taken a blue circle and I have cut this into 4 equal parts. I'll show you how these 4 are equal. Okay, let me copy this to a right side and make each of these sectors overlap one above the other. Did you see? All these sectors are equal because they perfectly overlap on each other. So in this case, angle of each sector will become 1/4 of the total rotation, that is 90 degree. Similarly, arc length of each sector will be 1/4 of the perimeter, that is 1/4 times 2 pi r. Instead of writing 1 by 4, can I write it as 90 degree or 360 degree? Yes, I can. Yeah. Okay. Area of each sector will also be similarly 1/4 the area of the circle, which is 90 over 360 times pi r squared. Okay, let's do this activity for one more circle. Here I have taken an yellow circle and then I've cut it into 6 equal parts. Let me just copy it over to the right side and place them one above the other to see if they perfectly overlap or not. Perfect. All the 6 sectors of this circle also overlap perfectly one above the other. So in this case, angle of each sector is 1/6 of the full rotation, that is 360 degree over 6, which is 60 degrees. So arc length of each sector will be 1/6 the length of perimeter of the circle, which is 1 by 6 times 2 pi r, which we can rewrite as 60 degree divided by 360 degree into 2 pi r. Same thing we can do it for the area of each sector. So each sector will be 1/6 of the area of the circle. So it will be 1/6 of pi r square. So it's again can be rewritten as 60 degree divided by 360 degree times pi r square. Let's do this activity one last time. This time I'm taking a circle and cutting it into 8 equal pieces. Even in this case, all the sectors of the circles overlap one above the other perfectly. You can see it to yourself. Okay, so let's write what is the angle of each sector here. Angle of each sector is equal to 360 divided by 8, which is 45 degree. So what is the arc length of each sector? So this is 1 over 8 times the 2 pi r, which can be rewritten as 45 degree divided by 360 degree times 2 pi r. Okay, area of each sector is again going to be 1 over 8 times pi r square, which is again equal to 45 degree divided by 360 degree times pi r square. So can we simplify it and then come up with an arc length formula? So for any given angle, arc length is equal to angle in degrees divided by 360 degree times the circumference of the circle, which is equal to angle divided by 360 degree into 2 pi r. Similarly, area of the sector is equal to angle by 360 degree times area of the circle. Now let's take 3 concentric circles centered at point O with radius r1, r2 and r3 respectively. Okay. Let me create an angle alpha degrees at the center of the circle. Now this angle creates 3 sectors in this system of 3 concentric circles, S1, S2 and S3. Okay. From our previous learning, can we write alpha over 360 is equal to S1 by 2 pi R1 is equal to S2 by 2 pi R2 equals S3 by 2 pi R3. Okay. For any given angle alpha, can we write S1 by R1 equals S2 by R2 equals S3 by R3? What that means is for any given angle, the ratio of the arc length to the radius of the arc is always constant. In that case, can we use this constant as the measure of angle? Well, absolutely we can. So this is the definition of radian measure. In radian measure, angle is measured as the ratio of arc length to the length of the radius. Look at this diagram. So we have an arc with length s and radius r. So we can write theta equals s over r, where theta is the angle subtended at the center, s is the length of the arc, r is the radius. By slight rearrangement of this equation, we'll get s equals r theta. So if we know that angle subtended at the center in radians and then the radius, we'll be able to compute the length of the arc as well. Then what is 1 radian? In this case, I've taken an arc such that the arc length is equal to the radius. So theta, we know that theta equals s equals s over r. Here s equals r, so theta is equal to 1 radian. So 1 radian is the angle subtended by an arc equal in length to the radius. Okay, let's look at this example. Here s equals 2 pi r, that is the perimeter of the circle. So theta becomes 2 pi radians. 2 pi radian is the angle subtended by an arc equal in length to the circumference of the circle. Radian measure is and what 1 radian is. Let's arrive at some of the formulas to convert angle in degrees to radian measure and angle in radian measure to degree measure. So in degree measure, one full rotation is 360 degrees. Likewise, in radian measure, one full rotation is 2 pi radians, right? Therefore, we can write it as degree measure divided by 360 degree equals radian measure by 2 pi. With slight rearrangement, we can rewrite this equation as radian measure equals 2 pi by 360 times degree measure, which can further be simplified into radian measure equals pi over 180 times degree measure. Similarly, degree measure equals 360 by 2 pi times radian measure, which can further simplify it into 180 divided by pi times radian measure. Now let's convert some of important degree angles in degree measure to radian measure. So for 30 degree, it's pi over 180 times 30, which simplifies into pi by 6. For 45 degree, radian measure equals pi over 180 times 45, which is pi by 4 radians. 60 degree is simple as well. So 60 degree simplifies to pi by 3 radians. 90 degree is pi over 180 times 90, which equals pi by 2 radians. For 120 degrees, it will be 2 pi by 3 radians. 270 degrees will be 3 pi by 2 radians. For 180 degrees, it is simple, it's pi radians. So 360 is 2 pi radians, which is full rotation that we had already seen. For all the important angles in degree measure, I have the conversion tabulated here. You can take a screenshot, and these are very important. I think this should be imprinted on your memory. Yeah, the same thing I have represented in a diagram form. So whichever is convenient, tabular form or the circle diagram, take a screenshot and then have a look at it every now and then until this is written in your memory. Okay, now let's test our understanding of the topic by solving some of the exercise problems in the text. In this video, I will be solving exercise 3.1 from the NCERT textbook, which is prescribed for 11th standard students. Our first exercise problem is find the radian measure corresponding to the following degree measures. First up, we have 25 degrees. We know the formula for radian measure conversion. So radian measure equals pi over 180 times the angle given here is 25 degree. With some simplification, we can arrive at the final answer. Radian measure equals 5 times pi over 36. Second problem, we have minus 47 degree 30 minutes. Okay, here before converting it into radian measure, we need to convert 30 minutes into fractional degrees, right? So how I do that, I'll take the absolute part of the degree plus I'll add the 30 minutes over 60, so which will become minus 47.5 degrees. So this is what I want to convert to radian measure. Now let's write down the radian measure formula. So radian measure equals pi over 180 times minus 47.5. So with simplification, we can get the answer. So minus 19 pi over 72. We cannot further simplify. So I'll leave the answer as minus 19 pi divided by 72. Okay, let's convert 240 degrees into radian measure. Let's write down the formula for radian measure. So pi over 180 times 240 degrees here. So 240 and 180 can be divided by 60. 60 3 times 60 is 180 and 4 times of 60 is 240. So let me do the appropriate cancellation. So the final answer is 4 pi by 3. Let's move on to another example, which is 520 degrees. As usual, let's write down the formula. So radian measure equals pi over 180 times the angle in degree. So angle in degree here is 520 degrees, right? 180 and 520 are divisible by 20. So 20 times 9 is 180 and 20 times 26 is 520 degree. So radian measure for this is 26 pi divided by 9. So in the previous problem set, we converted from degree to radians. Now let's do the otherwise. So first up, we have 11 by 16 radians. Let's write down the formula for degree measure. So here the theta given is 11 by 16. And for pi, I'm substituting 22 by 7. So I'm just making a rearrangement here. So 11, 1 times 11 is 11, 2 times 11 is 22. After appropriate cancellations, so degree measure is 39.375 degrees. Okay, this is good enough answer, but let's convert this fractional degree into a degree, minutes and second format. So for minutes, I'll take the fractional part of it and multiply it by 60. And I'll take the integer part of the minute that we got, which is 22. And for the seconds part, I'll again take the fraction part and then multiply it by 60, which I'll get 30 seconds. So now we have minus 4 radian to be converted to degree. Let's, as usual, write the formula. So degree measure we got here is minus 229.0909 degrees. Let's convert the fractional degree into degree, minutes and seconds format. I'll take the fraction part of the degree measure we got and multiply it by 60. And again, I'll take the integer part and then have the minutes. For seconds also, I'll do the similar calculation I'll take the fractional part of the minutes and multiply it by 60. I again take the integer part of that answer that I got. So let's convert 5 pi by 3 radians into degree. So pi cancels out with the pi in the numerator. Okay, so now we have 60 times 5, which is 300 degrees. Our last problem in this set is 7 pi by 6. Let's write down the formula 180 by pi times the angle theta in radians. So pi in the denominator cancels with the pi in numerator. So 6 and 180 are divisible by 6. So 6 and 30 times. So the degree measure equals 210 degree in this example. Next up, we have a very interesting problem. A wheel makes 360 revolutions in 1 minute. Through how many radians does it turn in 1 second? What do we have here? Given we have a wheel makes 360 revolutions in 1 minute. So we know that in 1 minute there are 60 seconds. Okay, let's understand and compute how many revolution it makes in 1 second. So it will be 360 divided by 60, which is 6 revolutions per second. We know that 1 revolution equals 2 pi radians. That is, revolution is nothing but 1 full rotation. So 1 revolution can be written as 2 pi radians. Now let's substitute and get the radians per second. So radians per second equals revolutions per second times the radians per revolution, which is equals to 6 times 2 pi. We have 12 pi as the answer here. Find the degree measure of an angle subtended at the center of a circle of radius 100 cm by an arc of length 22 cm. Use pi equals 22 over 7. Okay. So given r equals 100 cm and s equals 22 cm, we need to find out the angle theta. So we know angle theta is equal to s over r, right? So we have theta is equal to s over r, which is 22 by 100. Okay, so I'm keeping it as, I'm not simplifying it, I'm keeping it as 22 by 100. You'll see why. Okay, degree measure equals theta times 180 divided by pi. Okay, let's substitute for theta and pi. So we know theta is equal to 22 by 100, and in the question we have been asked to use 22 over 7 as pi. Okay, now let's cancel out 22 in the numerator with the 22 in the denominator, and 100 in the denominator. So okay, 100 in the denominator and 180 in the numerator is divisible by 10. So 10 times 10 is 100 and 10 times 18 is 180. So let's cancel out. So we have 126 degrees divided by 10, so which is 12.6 degrees. Let's further convert this value into degree and minutes. So we will get 12 degrees and 36 minutes. That is the answer for this question. In a circle of diameter 40 centimeter, the length of a chord is 20 centimeter. Find the length of the minor arc of the chord. Okay, let's draw out a diagram for this. Drawing a circle. So given diameter of the circle is 40 centimeter and the length of the chord is 20 centimeter. Let's draw a chord of length 20 centimeter in this particular circle, with starting from point A and ending at point B. We also know that radius of this circle is 20 centimeter because we know radius is half of the diameter. Right? Let's join the lines OA and OB. So this OA and OB will be 20 centimeter because these two are the radii of the circle. So now we have the triangle AOB, which is an equilateral triangle because all the sides AO, OB and AB are equal to 20 centimeter. We also know that the interior angles of an equilateral triangle will equal to 60 degrees. So that is angle AOB is equal to 60. which means theta is equal to pi by 3 radians. Now we know that theta is equal to pi by 3 and then r is equal to 20 centimeter. Let's calculate the arc length. So in this diagram, the arc is highlighted in color orange. So let's calculate it. So we know s is equal to r theta, s equals 20 and theta equals pi by 3. So we have the final answer as 20 pi by 3 centimeters. If in two circles, arcs of the same length subtend angle 60 degree and 75 degree at the center, find the ratio of their radii. Let's make a small construction just to visualize the problem. So we have a circle with the radius r1. So this is angle 60 degree. So we have a circle with the radius r2, in which the arc is subtending 75 degrees. Given that arc lengths are equal, so s1 equals s2. We know s1 equals r1 theta 1 and s2 equals r2 theta 2. Right? So let's make substitutions for r1 and r2 and theta 1 and theta 2. So since let's cancel out the factor for converting degrees to radians because we have it on both sides of the equation. So now r1 by r2 becomes 75 degree divided by 60 degree, which is equal to 5:4 ratio. So r1 is to r2 equals 5:4. So this is the last question of the exercise. Find the angle in the radian through which a pendulum swings if its length is 75 centimeter and the tip describes an arc of length 160 centimeter. Okay. Now given the length of pendulum is 75 centimeter and arc length is 60. So you can visualize the problem in the diagram here. So now we know that theta equals s over r. Let's substitute for s and r and we get the final answer. The second case, s equals 10 centimeter. So we know r equals 75 and s equals 10. Let's compute theta. Theta is equal to s by r. So that is 10 by 75 centimeter. So that is 0.13 radians. Now in this problem set, the third problem is s equals 15 centimeter. So given r equals 75 centimeter, s equals 15 centimeter. Let's make the substitution. Theta is equal to s by r, so which is equal to 15 by 75, which is 1 by 5. That is 0.2 radians should be the answer. Last problem of this last problem set, we have s equals 21 centimeter. Given length of the pendulum is r, which is equal to 25 centimeter, and arc length s is equal to 21 centimeter. So we need to find out theta. Theta equals s divided by r, which is 21 divided by 75, which equals 0.28 radians.